Okay, everybody, welcome to the next session. Here we are for the Introduction to Photogrammetry lecture. We're going to cover the basics, okay? So starting from scratch, you know a little bit about drones, how they fly, um, general. Some of you know a lot of the rules and some photography basics. Um, and that's good. That builds a good foundation. But now we're going to get into the what's called photogrammetry, which is the technique. Um, it's like a sub-science of remote sensing, um, and this is going to explain, uh, like I said, this theory of when we get out into that field and we collect data and then we process it, all of the things that you're going to learn here are what the software is doing in terms of background processing, and when the flight capture happens, it's based on these theories, etc. Okay, so without further ado, here we go. Okay, and let's talk about what is photogrammetry. Um, Break it down in a definition. Uh, Try to make this as simple as possible, although it's not going to be, just because it's such a long word with a lot of things going on here. But what we're going to say is this is the science and technology of obtaining spatial measurements and other geometrically reliable derived products from photographs. So that means that we're going to use photos to uh, build something or come up with something beyond just the photograph itself. Measurements, right, are a really important component of this, because when things are geometrically placed in a precise manner, and we'll learn how that happens here, then proper measurements can be made. And so if we put a bunch of photographs together and we mosaic them in a way that everything becomes one large picture per se, where our geometry is correct and we have derived this end product, we end up with something like a map, right? And that's really what we are pulling off here. Um, the photograph can become what's known as a base map, and you can draft on top of that base map. So if it's utilities or whatnot, you could be drafting um, road networks and paint stripes and curbs and gutters and whatever the case may be, right? Whatever the photograph has on it, or and the objectives are. Um, okay, so photo light, right? Gramma, something to draw, as I was just mentioning, and then metron, that's to measure. So those are your core elements of photogrammetry. Okay, now just a brief timeline about how all this has gone down over time. We go way back into the middle 19th century, and we have to first look at aerial photography in general. And this was from a French guy named Nadar. Okay, and he was the first one to record taking a picture from an aerial picture from a hot air balloon. Okay, um, yeah, and then, as technology got better, I mean, it seems like it takes a long time, at least on this timeline, but we fast forward about 50 years or so. And in the 1900s is when the Wright brothers came up with planes, and so they um, uh, started attaching um, cameras or sticking cameras out of planes to take pictures as well, right? And so Eureka, you have this discovery of aerial photography. Now, in World War I, you go, okay, how can this actually be used in a practical sense? And it was certainly used in military operations um, for scouting missions, to see the enemy, to see the trenches, where their bases were. And it's like mapping in wartime was kind of a much more readily available advantage in that instance. So we move past World War One, and like many things with technology, you move from military to civilian applications. Okay, so there's uses in civilians. There's use in the civil world as well, like for engineering, for surveying, you name it. Okay, then World War II, we have advances in image technology, where like if you're taking remote sensing, you'll learn about infrared pictures or infrared imagery. So seeing beyond and allowing to scout even more things that are unseen. Okay, so keep going. We move on. We have advances in technology where photogrammetry is being produced on these large mechanical type of machines. Okay, hard copy type of machines. The photos come out as what are called stereo pairs, 9 by 9 size contact prints. So from film, okay, film in a dark room. I actually did this before, believe it or not. You might say you're not that old, but I guess I worked at a kind of a legacy firm when I first started, and it was quite interesting. Fun place to really kind of cut your teeth when it comes to this kind of science. So that's really kind of old school, to be honest with you. Now moving into the, even past the 90s, into the 2000s, photogrammetry was digital, right? And not just what we were seeing or post-processing in a digital way, like we see in this picture here. But photogrammetry, by the way, all these other things were not drones, right? They were large aircraft. Um, so just so you know, photogrammetry is not a drone thing per se. Um, yeah, but that's why I kind of present this. But everything moves to kind of this digital formats, and as well as the cameras. The cameras become digital as well. And fast forward a little bit more to about the 2010s time frame, and that's where you get to drones. Okay, drones is about a 10 year, a 10 year, 10, 12. You might say 15, but I would say, and I'm recording this in 21. Okay, 2021. You might say 15 years, but really it's about a 10 year history where drones had their own kind of place, and photogrammetry became not a ubiquitous use case, but one of the um, practical uses. And as that practicality became easier to use and with less resistance, then we get to like where we are now. Okay, um, so moving on, when we talk about the conventional methods, right? I want you to really kind of look at the graphics that I have in these pictures. Um, what we see here is, okay, imagine what we're looking on the left, and these little red lines. It's like they're connecting two dots on the bottom. And so the bottom, imagine this being some type of terrain or surface, and then above we have photographs. Okay, and those photographs would be pointing straight down. Like, actually, let me show you an example. Okay, so I have a camera here, and camera pointed straight down like this. Okay, that's how we're going to, that's the conventional method of collecting photogrammetry. Okay, aerial photogrammetry in particular. And so this position here is called nadir. Okay, Nadir. Okay, straight down. um, let's see. So what happens is when we capture pictures in this type of format, um, the what we're trying to achieve is some type of redundancy, so that we can match those pictures together. Okay, and then by matching those pictures together, we are able to process or we're able to create these measurements and things that I mentioned earlier about what makes up photogrammetry, right? The term itself. So let's see. I'm just going to move on and try to explain this as we go through here. Overlap is the key to this working, okay? So overlap between the photographs. As the, I know this is a plane here, and it could be a plane, it could be a plane, it could be a drone, doesn't matter, honestly, because this is just the theory behind it, right? So as a platform is flying, what needs to happen here is that our pictures are being taken in a sequence, okay? Boom, 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 boom. And so this sequence would be in a very precise manner, and that these pictures are taking in very straight lines, okay? So the drone's not going to be wiggling back and forth, okay? And the camera is also going to be in that nadir position the entire time. So as the drone is flying along, okay, the overlap between the pictures is creating redundancy, okay? So then those redundancy allows for the matching of features, okay? Features. When I say feature, I mean like a thing. So let's say something on the ground that like a trash can on the ground, right? Well, that's a feature. Or a I don't know, a bush. That's a feature. So the more times that those features show up in multiple images, okay, so the more times those features are redundant, the more overlap, and let's say the better case of this justification, then is going to exist. So yeah, this is conventional, like with large aircrafts, and before UAS, the overlap percentage we call, here, I'll use my mouse to try to demonstrate this, like from 1 to 6, okay, in this direction. I know these don't look like straight lines, but they, for all intents and purposes, are supposed to be. So from 1 to 6, okay, we would call this front overlap or forward overlap, okay, because it's as the drone is moving forward, okay, and imagine that, I know that I've got an angle here to this, but imagine that I'm like where you are is you're the ground. So it's like moving forward, boom, 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 boom. That's a picture being taken, or those are pictures being taken, okay? Now, 1 and 12, 2 and 11, et cetera, those are what are, that's what's called side overlap, okay? Side overlap. So that would be like from this line, then this line, okay? And so these two, notice how where my hands are. Now they're on top of one another. And then if we did it again, now they're on top of each other. And then if we did it again, now they're on top of, right? So that's side overlap. So it's in two directions, both front and side. Those are the forms of overlap that are going to create lots of redundancy as of features. And so by having all of that redundancy, we are then able to create matching, we're able to run matching algorithms where the computer is able to detect these features and match them together, okay? So we're getting there, all right? We're getting there. Conventional as well, I wanna mention this, it's important just as where we came from. And this is still exists with large aircrafts today for the most part. Cameras on large aircrafts, manned aircrafts are of much higher quality and expense in general, and so they are able to overcome some of the they don't need as much overlap because they're designed in more specific ways, whereas drone photogrammetry is not necessarily, that's not necessarily what they made like on a Phantom, the camera, for photogrammetry per se. But what I'm trying to say is, with a conventional overlap methodology, we would be collecting 60%, okay, 60% like this forward, and 30% on the side, okay, 30% on the side. I mean 60% here. 60% of this area would be forward overlap, okay, or front overlap, okay. 30% of this would be the side, okay. Now, this probably does a better job of actually explaining that. In this graphic here, right, we have, looking at this from a straight down perspective, here's your UAS overlap. And I mentioned this already, right? As the drone is flying forward in a forward position, it's capturing its photos in a very precise sequence. So look at how straight these lines are. We call these flight lines, okay? Flight lines. And these are very straight lines, okay? We're gonna program our drone flight software to fly lines like this for us automatically, okay? But yeah, instead of 60% going forward, we have to capture a little bit more because our camera quality is not as good. So more redundancy is going to make up for discrepancies in camera quality. And in this case, we're going to go with a 75% forward or front overlap, okay? 75%. And now, parallel lines are going to create side overlap, okay? So forward overlap is as the drone is flying in a straight line, and it's as the pictures are being taken in sequence in the same line. Side overlap would be side by side, right? Pictures that are side by side, okay? And side overlap. And so in that case, we're looking at a 70%, 70% side overlap. These numbers, you can we can change these before we fly or after we fly, like between mission to mission. By the way, this is called a mission, okay? We're no longer just going about flight operations. This has a specific term called a flight mission, okay? So, um, yeah, between flight missions, if you tinker with this kind of stuff, it's it's fine. I'm telling you the best recommendations from my experience. I know there's a lot of other information out there on the internet, um, but you would not change these values during a mission, okay? Because really, the thing with photogrammetry is, okay, it's a different way of thinking as opposed to like just traditional photography. With photogrammetry, we're really wanting every photo to appear the same, okay? Like, and I mean the exposure and the shutter and all that kind of stuff, okay? And the really important part of this is having the right amount of overlap, okay? And a consistent amount of overlap throughout the mission, okay? If that stuff kind of breaks down or is inconsistent, you end up with problems in the project, right? Um, Okay, let's move on. So this is called multi-ray photogrammetry. It's just a fancier word compared to the conventional types, but multi-ray is the same type of aerial triangulation type of math that we saw a few slides ago, okay, the matching of features. But with multi-ray, this is now that 75 and 70% overlap. Um, uh, as compared to the 60-30 ratio. And so this creates a much higher level of redundancy of these features. And, basically where we're at is we have computing power, modern computing power with um, really advanced matching software that is able to derive these photogrammetrically these photogrammetry type products. Okay, 3D products. It's actually quite amazing. So what you see here, just in the picture, right? Let me try to just break this down. Up at the top, these are your pictures, right? This is post. This is a post uh, screen screen capture of a project that has been processed and it's post-flight. So we have the uh, images up here at the top. We have what's called a point cloud, which is essentially the product that is derived, okay, one of the products that is derived from this photogrammetric process through images. And then I like this because it highlights like this little, or all these little green lines are kind of splitting down here. Um, remember, I just mentioned the word aerial triangulation. Try to break that down. Triangulation, okay? Triangulation is how the matching of these features come together, because we've got similar features being found and matched, and so then they are triangulated via this via where they existed in space. That triangulation creates one singular point, and so like for example, that's what this would be here, and in reality, what we're looking at with this whole scene here is like millions and millions and millions of these points that we're driving. Okay, Um, so yeah, let's check this out. We have how it comes to this, right? The software. Okay, breaking down what happens during photogrammetry software. Photogrammetry process, the software when it's processing, okay? The software first identifies unique colors, okay? And it colors and or textures, okay, in a photograph. And then it generates what are called key points, okay? This is photo by photo, okay? Single photo by single photo, not taking into consideration the overlap or anything so far, okay? So what I wanted to show you here, imagine that these little orange crosses, and imagine these are our key points, okay? So as the software is identifying, this is just pattern recognition, right? It's looking through and it's trying to recognize, okay, where are unique colors, okay? Where are unique colors? So from color here, from color A to color B to color C to color D, is there some unique patterns there, okay? And if there are, I'm gonna stamp it like this, okay? I'm gonna stamp it and create a key point on that unique, where that unique color exists in a photograph. And that's what we have here. We have a whole bunch of these photographs. We have a whole bunch of key points created in this image example. Now, check this out. I'm gonna do something here. Imagine we have two photographs, okay, uh, that have overlapped each other, okay? And I know this doesn't look like a lot of overlap, but I'm going to try to do a little something to demonstrate. But imagine as we look at this, okay, we see key points in each of these, okay? Key points in between these two photo examples, okay? And what I want to highlight to you guys is if we overlap them like this, the only place where the key points stick to one another. In other words, it's the same key point in two different photos, i.e. it's the same feature in two different photos, okay? And then they're matched together. That would be this little example here. So let me try that again, okay? So imagine we've got two photos here, and this is where they exist in real space, but then over the same scene, it would look something like this, okay? And so what I've done, we'll come back to this in a second. Um, let's keep focusing on this idea of key points for right now. Okay. When it comes to the software creating these key points, remember these are unique colors, so things that have a lot of variation, right? Heterogeneous in nature. That means that there's a lot of variety, okay? Things that are still and they don't move, okay? So a person riding a bike through a scene is not exactly a good example. But a stationary building that doesn't move is a great example, right? The corner of a building, that's a great example. The flatter, okay, and like the more diffused the hue or the brightness of, and I'm not saying dark, I'm saying you know, as opposed to glossy or reflective type of feature, the better off software is going to have, better job software is going to do at finding these key points, okay, finding these key points. And these are good examples like rocks and gravel pits and quarries and even urban areas are really good examples. So this should help you recognize, okay, these don't work as well, okay, at the software creating these key points. I just call them challenging type of features, things that are very similar in color or homogeneous in nature, okay, or things that are moving, or things that are highly reflective, like this or that. That's, you know, opposites here, apples and oranges. Think about like a sand dune. What does it all look like from the air, right? It kind of all looks the same. Or moving over to the right side, okay, water. With water, you have, not only does it all look the same, but it's moving frequently, right? Especially if there's waves, and there's a very good chance if the sun's out that it's going to be reflecting. So water is like the ultimate challenging surface when it comes to photogrammetry processing. And I'm not saying these things are impossible, but I'm saying these types of these types of features will cause the software will cause photogrammetry in general have a hard time of creating matches, okay, to generate key points and or pattern recognition, I should say that to create these patterns, unique patterns. Trees and vegetation also very, very much in this category. All right. Now let's go back. I kind of jumped around there, and that wasn't a very good one. So let me try to revisit what we were just looking at. Remember I went to here and I did this kind of thing, okay? And I said, oh, look, this is the only one, the red circle is the only one where it's the exact same key point twice, okay? It's the exact same key point twice. Now, if we fast forward to this portion of the processing, okay, we end up with one singular result. And I'm not saying we end up with one photo, I'm saying we end up with one singular, after all of the key points are generated, the next part of the process, this photogrammetry process, is to actually perform the matching of the two things and triangulate where exactly are these things existing in space. And so this method, we would be finding, okay, here is, like we just saw, key point one in image A. Here's key point one in image B. We match them together. We end up with one singular result, okay? One singular point. And then that point is called the tie point. Specifically the automatic tie point, because it is generated automatically, right, through all of this matching of these key points. Okay, so the resulting automatic tie point after the aerial triangulation, all right, and the overlapping area of the two images displaying the resulting, oh, I'm sorry, the left side is showing now, like, notice there's a lot less of those orange crosses, right? Because inherently, there's going to be less automatic tie points than there are key points. That's normal, okay? And so that's fine. That's the result of what we're seeing here. This, let me back up 1 second. This here is more than just the automatic tie points. I mean, ultimately, or originally from the beginning, yes, it was. You could think of your automatic tie points as, because it is the very first process during the photogrammetry type of processing, you could think of the automatic tie points as the skeleton of the project, okay? It's like building out the framework of what everything else is going to look like, okay? So this example is actually called a dense point cloud. So it's like we have all the framework, but then we built everything else on top of it, right? The point I'm trying to make here is that you have to have, number one, solid key points. Then number two, a sufficient amount of automatic tie points that came from those key points, okay, that were matched from those key points. And then three, if you have those first two things, the rest of the build out during the processing, the rest of the build out will be in a much more solid state based on that, okay? All right, let's keep going. How does the software know? How does it know? Yeah, that's a kind of a layman's question, right? How does it know? Well, the photogrammetry aerial triangulation, it's based on, we're going to get into now looking at camera and sensor specific type of, topics. It's based, how does it do this matching, right, to create these key points and ultimately match and then know, like you saw that query, how did it know that this part of the mountain is there and this part of the mountain is over there and this feature is over here, et cetera, et cetera. It looks at internal camera specifications, okay? And really three things. The focal length, which is generally stated in millimeters, okay? And the focal length is a big one because that's going to determine what altitude, okay, the drone is gonna fly above ground level. So here's a focal length as an example, right? You have like a image sensor, and then from where the image sensor is to where the end of the glass on the camera, that's called the focal length. So here's my little trusty example again. Okay. Okay. Let's see. Let's try to do this like that. There we go. Okay. So my camera's sensor is somewhere in here. Okay. And the end of the glass is about right there. So that distance from there to there is the camera's focal length. And this is a fun camera because I have a dynamic zoom, an optical zoom, where I can change the focal length by doing this. If it's not, there we go. Okay, I was moving it the wrong way. Okay, so right, this is what you might consider zooming in and out. That would be zoomed out. Here we are zoomed in. What I've done is I've changed the focal length to make it much longer now. Okay, much longer now. It's like a telescopic, range. Um, what do you do with a telescope? When you have a telescope, you can see things that are very far away. It's like having a very long extended focal length. The focal length is an important piece of this, okay, for the software to know what it's doing. And I'll explain this a little bit more as we go on here. The next thing is that the software looks at the physical dimensions, again, in millimeters, the physical dimensions of the camera's sensor. And it uses this to determine coverage on the ground. So like geometric positions on the ground or in the scene, right? This is called the image footprint, the image footprint. So what relates to how the image was collected, how that relates to what was actually collected on the ground. That would be size-wise, that would be called the image footprint. And here's the example of that over here, right? Physical dimensions in millimeters. You have the X direction like this, okay, horizontal, and then the Y direction here, vertical, okay? So the physical size of that, the physical size of the sensor. And also it looks at how many pixels exist in that sensor, right? Megapixels, we'll get into that here in a minute, but that plays a role into this whole technique. And then the last part is called the distortion values. So you have, let's see, radial versus, actually these are both radial types, but there's something called radial and there's tangential distortion values. And so those are going to determine various angles. And basically, you're always going to have some sort of distortion that exists with any camera and with any picture. But the camera manufacturer has understood that, and they have either put that into the camera's metadata somehow. Um, uh, you don't really see it with the eye, but it's there. Okay, it's there. We're not going to focus that much on the distortion stuff in this course. Um, really, with this lesson, we're gonna really hone in on the focal length and the dimension part. Okay, I just want you guys to know that there's these three major things that the software looks at. Okay, so this combination of these internal specifications that the software is examining. Okay, and the tie point creation. All of this stuff combined, we call that the bundle block. Okay, the bundle block. Okay, there we go. I won't ever have you guys. I don't think I'm going to have you examine a bundle block. It's a lot of numbers and letters and other things that mostly numbers because it's math, and even I don't examine those myself. But yeah, now you know what it's called if we want to be specific about it. Okay, this question comes up all the time, and you might be thinking it now. And here's how we're going to explain this. How high should I fly? Right? How high should I fly? What difference does it make? What should I do? Well, how high you fly, okay, there's going to be a number of things that are going to have you determine that. FAA and airspace, um, protocols, rules, or restrictions not considered. How high you fly is based on, um, well, we'll see here in a minute. Number one, what's your intention and your goal in terms of How much detail do you want to resolve from the pictures? But number two, and this is like the math side of things, okay? Um, how high you fly is going to be determined by uh, the camera's focal length. The camera is what's called pixel size. Okay, so that would be the fixed pixels inside the camera. Okay, like if you have a camera that's a 12 megapixel camera, it's going to be 4,000 pixels this way, 3,000 pixels that way. So what is the physical size of those pixels? Okay, so focal length divided by the camera's pixel size times 10. I'm just reading off this formula here. It's a simple formula, ultimately. We have altitude here. This is going to be your how high you fly. Now, these 1, 2, 3 things, these are going to be fixed, right? You're not going to change those. It's going to change from camera to camera if you have different models of camera or different models of drones. But if you're using the same drone every time, this and this is going to stay the same. This right here called the GSD is going to change. And we'll get into that here in a minute here, okay? But when this changes, ultimately your altitude is going to change as well, okay? Here's it broken down, all right? We have like the focal length here, okay? From the camera sensor to the, and this is an expanded view, but the camera sensor to the end of the glass. And then you have your, your flying height, whether it's above sea level or above ground level. Let's just use this one here, big H minus little h. Yeah, that's how these things are going to play. This formula is going to ultimately determine what this is going to end up being, okay? So what I'm trying to kind of get to you guys is that there's a relationship, a direct relationship between altitude and ground sample distance. So what is ground sample distance, or GSD? Okay, GSD. All right, GSD is the pitch or the side of a pixel. Okay, and we're talking about now after we've taken a picture and we look at one of the pixels, like zoom into one of the little pixels on the picture, and that pixel as it's normalized to the real world. Okay, what is its value? So in other words, if that pixel measures out to be, right, the pitch or the side, that's what we mean by that, right? If one of those sides is 1.5 makes up, okay, a utility on the ground that is 3 inches long, that means that the GSD for that pixel is 3 inches, okay? Whatever it is. And let's go back for a second. The higher you are here, right, the larger this number is, the larger this number is going to be, and vice versa, okay, and vice versa. So we look at GSD, or we classify GSD in two kind of categories. We have a coarse versus fine, and really there's a lot of in between, right? I'm just trying to give you guys the examples to demonstrate in this case. But this is the same scene between the left side and the right side. And with our coarse GSD, okay, imagine that each one of these pixels here, the size of each one of those pixels is 25 centimeters across, right? The side, right? Either this way or this way, 25 centimeters. Then on the other side, where the fine pixels are, you have 2.5 centimeters. So 10 times reduced in size in terms of its in terms of the side there. Think about this for a second. All you have to do is look at, I mean, it doesn't take that much to actually contemplate what's going on, right? It's like low res, old school TV versus ultra high def, right? When we look at a 4K, 8K, whatever K this stuff is, they're talking about how many pixels you have. And the more pixels exist, the higher the resolution is going to be. So it's the same concept here. The smaller the number is for the GSD, the finer those pixels are going to be, or the smaller they're going to be, right? It's like fine, like a grain of sand. The finer the grain of sand, the softer, the smoother it is on your hands. The coarser they are, the bigger the pixels are, right? The bigger the pixels are. Now, what does this all mean? Well, I'm talking about detail here, detail. So remember before I said, how high are you going to fly? And you have from a kind of a holistic approach, kind of question and answer here, what's the purpose, right? What is the purpose? Is it to capture a lot of detail, or is it to capture, let's say, a larger area? You might say both, because that's another factor in this, okay? But yeah, I wanted to get this point across. This is a really important part, and we're going to refer back to this often, okay? Let's see, we did mention here, collective sense. This is another way of saying spatial resolution, okay? And it's kind of a traditional way of saying this, spatial resolution. So here we could see these examples again. Again, it's like low def versus high def. Low spatial resolution, medium versus high spatial resolution. The amount of detail that is resolved, okay? That's where resolution ultimately comes from. Resolved. What are you able to see? What can you pick out and determine? That would be the resolving power. So higher resolution means there's more detail, okay? Now, as we compare GSDs to each other, coarse versus fine. With coarse, we've got less resolving power and less detail, right? Versus high and more. With the coarse, you've got smaller file sizes compared to larger file sizes. The larger file size with a fine GSD exists because, well, there's more pixels, like exponentially more pixels, okay? Every time that the GSD increases by 1, okay, the amount of pixels actually increases by 4. So what I mean by, like, if you go from 1 to 2, okay, you just went from a surface area that was 2, let's just say inches, you know, in squared, to 4 inches squared, right? To 8 inches, to 16 inches squared, to, right, 16 times 16, or that's how, no, 16 times 4, that's how it works. Sorry. But yeah, so that makes a difference. These are things that, as you get more into this, you start asking yourself as far as considerations are concerned. And, you know, to kind of go off topic a little bit, when it comes to, like, if this is going to be business or this is going to be something that you're on the clock for, you have to consider the finer this stuff is, the more time it's going to take, because we've got larger file sizes, okay? You're also going to be flying lower. You have to fly lower. So a lower altitude means finer GSD, plain and simple, okay? But when you fly lower, that also means you have to capture more images for the same size of the same area size, okay? So that's more time. Accuracy-wise, you're talking higher accuracy and more, or I'm sorry, higher accuracy, more precision in the finer GSD as opposed to the coarser GSD. That goes back to the whole resolution thing. With models, you get a sparser versus denser model, meaning that you get a lot more points because there's more detail, right? With the finer ones, there's more pixels for the software to sort through and create these models for you. But the downside is you're talking larger or longer processing times for more images as opposed to faster processing times. So these are the give and takes that exist between you know, these different classifications of GSD. And again, I'm not saying they're always going to be a coarse versus fine example, or it's always going to be 25 versus 2.5, just showing these ends of the spectrum per se, right? Let's talk about megapixels, okay? So, like I said, the X versus Y sensor dimensions are important. And what happens is you have an image sensor has a fixed number of pixels in the X and a fixed number of pixels in the Y. And so this means that, let's say you have a sensor with 4,000 columns, okay? And so that would be in this direction. I know a column goes like this, but as you're counting them, you would go horizontally, okay? So 4,000 columns, that would be the X. 3,000 rows, that would be the Y, okay? If you take 4,000 and you times it by 3,000, you end up with 12 million. 12 million is how you end up with the abbreviation 12 megapixel camera, okay? 12 megapixel camera. If you ever want to figure this stuff out, as far as, you know, hey, I just took a picture, what kind of megapixels does it have? You could pull up, you can highlight pictures inside of like Windows or wherever Explorer, Photo Explorer you're looking at, and look at the metadata. And if you pull up the details, look at this. Here's the width and the height, okay? The width would be considered the X, the height would be considered the Y. And it's always gonna be there. Yeah, it'll be there because it's part of the camera's metadata. It's built into the, you know, what happens after the picture gets taken. And you also get focal length and other things like exposure time, f-stop, or aperture. Here's your shutter, ISO, etc. Right? Now, this is, I want to kind of debunk some misconceptions here because it's common to think that a higher megapixel is going to mean that you're going to get a higher quality picture, right? And that's not necessarily the case because with cameras and photography, the amount of light that that sensor can adjust to is really important, okay? So the range, in particular, we call it the dynamic range of how that camera adjusts itself is really important. The higher that dynamic range, the more contrast and the more detail, the more sharpness, etc. things are going to come out. So the higher dynamic range, you're going to yield better registration of light. So larger sensors, I'm talking physical size, okay? The larger the sensor is, and the on the camera itself, you're talking about larger fixed pixel sizes, okay? So like a 20 megapixel camera here versus a 20 megapixel camera, and I'm just using this as an example, versus a 20 megapixel camera here, okay? One is going to have a very, very small sensor, even though it has 20 megapixels. One is going to have a very, very much larger sensor, and this is comparisons saying. But this larger sensor is going to yield much higher quality pictures, okay? Much higher quality pictures. Let's see, 12 megapixel sensor with the size of 4/3 of an inch is superior. Okay, I'm reading this as we're looking at this. Is superior to a 24 megapixel sensor with a size of 1/2.3 inches. You know, what does that mean? Well, so 4/3. Look at these examples here. Look at how much larger the surface area is on this sensor, the 4/3 sensor versus the 1.23. Okay, even though this technically has more pixels in the sensor itself, those pixels are much smaller, meaning that the range of adjustment is much, you know, not as high of a quality. In other words, okay, when you're observing cameras, megapixels is not the be all end all. It is an important part of it, but it's the sensor size itself that is ultimately going to be a better, is going to determine image quality. Okay. Yeah. Okay. Let's move on to image footprints next, right? And so an image footprint, like we said, it's like when one picture is taken, and how does that relate? What's the relationship between that one picture versus the size of that one picture versus the size on the ground, okay? Um, let's see. So how large is the image footprint area? And we could determine that. And this is, again, these are things that the software is looking at as it's figuring out the bundle block, okay? So if we could first determine the length of the footprint in the X, then if we could determine the, actually I should have put, sorry, I'm going to edit this in the moment here. Let's say the width, because that's more appropriate terminology. Width and height. Okay, so if we can determine the width of X, and then we can determine the height of Y, we can times those two things together, and we end up with the footprint size, okay? So your footprint width, if we determine this in meters, here's our formula. We have altitude times, okay, 10 divided by, and again, look at the brackets here. We have to go back to some algebra here. It's like basics of ninth grade algebra. 10 divided by the focal length, okay, times your sensor's X size, okay, in millimeters. Okay, I'm not saying how many pixels there are, but I'm saying the physical size of the width, and then times 0.1. Okay, now there's a lab component of this, and I explain this a little bit better, like how to do this. But it's pretty straightforward once you get the math part down, like the formula, and go back into algebra days, and you go, okay, this is how the order of operations is. Once you figure out the X, then you figure out the Y, you just times them together, boom, now you know what that footprint's gonna be, okay? All right, let's look at an example that I have of manned aircraft versus drones, okay? Because I know this is drone class, but again, this whole topic is photogrammetry, which ultimately doesn't actually matter what acquisition platform we use. Now we have an example here of the Las Positas College, okay, in Livermore, roughly 111 acres in size. So it's this kind of shoe or foot-shaped property here, okay, that you see on the screen. Yeah, let's see. So on the manned aircraft, and these were taken different years. That stuff is not necessarily important here. Let's move on. Looking at our image footprints, okay, the data acquisition. Our manned aircraft, by mandate, as what, in addition to what's practical, but by mandate, it has to fly at, and it's actually supposed to be a minimum of about 1,000 feet. They were a little bit lower than that, but, oh no, they're at meters, sorry. So they're a little more than 3,000 feet in this example. So imagine that, right? How high they are, 3,000 feet. We kind of stretched this picture out, but look at the footprint that the manned aircraft was able to pick up here. We're talking the entire football field and the track, a lot of the parking lot, some of these exterior buildings, etc. Now the cameras are not one-to-one, okay? You've got a much longer focal length with this one, this Canon 5DS, an 85 millimeter focal length, versus the Sony camera, which is more like this type of camera, okay, handheld camera, on the UAV with a 16 millimeter focal length. You've also got larger sensor size and a larger megapixel out of this Canon versus the UAV equivalent. It's going to be very difficult to find a UAV or UAS example where the camera is much bigger than this example, because physically they can't handle payloads that are much bigger than something like a handheld camera, okay? Yeah, so check this out, right? We're saying 3,000 feet versus 100 meters, which is about 300 feet, right? Let's see. The thing that is important here is that GSD between these two is virtually identical. Okay, is virtually identical. That's a very important part. If we're saying apples to apples, that has to be the one thing that's synonymous between the two things. Okay, so that is the case in this example. And what I mean by that is we're seeing the exact same amount of resolved detail between these two platforms. It's just one is going to fly and capture much differently than the other. Okay. By the way, look at how many pictures this one takes versus this one. Okay, same area, same area. This comes down to footprint, folks. This is footprint. Okay, I know it says UAV, unmanned aerial vehicle, but the UAS has smaller footprints due to the camera type and the lower altitude. The DPI thing is not necessarily important in this, but the UAS also requires more forward and side overlap. Yeah, as we talked about. Okay, so here's the flight lines between the two. Here's the manned aircraft flight lines, right? Here's the UAV or drone flight lines. Okay, and look at how much different we're seeing these. And this is just the plan. This is just the plan out of it. But look at how much different you're seeing this, right? The other thing, little nuances to pay attention to here. We're talking about what's called seam lines. Okay, when you take in all these pictures, hundreds and hundreds of these pictures, what we're really trying to say, like we talked about at the beginning, was if we put them together as a mosaic, okay, as an end product, it gives us a really nice end. It gives us a really nice result. Well, what happens is when you put those into a mosaic, you end up with seams in between those photos, right? Seams here, right? Like this little space between them. The software doesn't always get it exactly right. So with the drone, what you end up happening is more instances of anomalies or artifacts like this, okay, where the seam is not going to line up exactly right, okay, exactly right. So it's going to take, it would take more human labor and intervention to correct this type of thing, right? In like a post process in the software, okay? Whereas something like the manned aircraft, because it captured such larger footprints, then the scene is going to be a little bit more ubiquitous in terms of like capturing, you know, all of these solar panels in one shot, right? So I'm not saying, again, one is better than the other, but just making this stuff kind of known to you. Okay, this is the last slide we have. And let's compare the two things. Now, I know this says, this is a typo here, because these were exactly the same spatial resolution. But our image footprints, well, let me back up. With the drone, you will have, I guess, more of a dynamic choice when it comes to spatial resolution, because with a fixed manned aircraft, you're kind of stuck with the lowest altitude that the thing can fly, right? Based on wherever its airspace is going to be. Whereas with the UAS, you could fly at 20 feet above the ground, right? And capture down to less than a centimeter in spatial resolution, GSD, okay? So that's kind of what that's saying there. Image footprints, we saw. UAS is much smaller image footprints versus manned aircraft. Also meaning that it has to take a lot more photos to capture the same area of interest, okay? But with the drone, you have like a more on-demand image collection, right? That's what I mean by this dynamic, you know, let's go get it tomorrow, right? As opposed, or let's go get it this afternoon, as opposed to, hey, a manned aircraft, you got to fuel it up, you got to find a pilot, etc. All these other things. Cost of flying a UAS initially, like on a project like this, which is a relatively small, I know it might seem like a whole college, but it's not that large of an area to map, is going to be a lot less flying a drone compared to a manned aircraft, right? The fixed cost of just getting a manned aircraft into the air, you're talking thousands of dollars, even just to fly a circle and come back, right? And then there's other things like when it comes to time of collection and processing, there's more, there's variables. There's so many variables involved that you could say, well, the UAS processes the images faster, or the images, the UAS example processed the images faster, but there was more post processing manpower required, right? So those kind of things are a little bit of have a little bit of variation between them, and I can't give you an exact fixed answer there. So some of these unanswered questions, you know, you'll come to terms with them as we go through the course. That's my hope and my goals. Um, and you'll find that the answers, a lot of it is situational and kind of circumstances. Okay, this and that kind of, you know, situations. Now we're obviously going to be flying all drone stuff, but I wanted to make this comparison so that you understood, you know, that there is other solutions out there as well. Okay. Ultimately, was the photogrammetry lecture, so it doesn't matter where you come, where it comes from. But yeah, with drones, we're going to be doing, we're going to be exploring a lot of this, a lot more in the semester, and so it's going to be fun. I think you're going to really enjoy it, especially once we get out there and go in the field, collect this data. We're going to go out and collect data. And you're going to be planning missions like this, and you're going to see it all kind of come to life over the semester, okay, over this course. Thanks so much for watching, everybody. Have a good rest of your afternoon, and bye for now.